Hello. Yes, as was said, my name is Evgeny Mandrikov. You also could find me, well, on Twitter, or should I say X, under the nickname Godin. Today's talk is about JVM, one not so well-known JVM feature, dynamic constants. And welcome, and let's start. Before I start, I should give you a disclaimer. I work in a wonderful company, SonarSource, creators of product Sonar. You might know them, by the way. Who knows? Who uses SonarLint, SonarCube? Wow, impressive. Well, nevertheless, company is great, but whatever I'm going to tell you today is not at all about this company. Whatever I'm going to tell today is connected to my, let's say, night job, to the open source project on which I work in my spare free time. And company can only dream that it owns my opinions. So today we're going to talk about JaCoCo, Java Code Coverage. We developed this tool for quite a long period of time, and there is a lot of Java versions, Java releases happened since then. So nowadays we test it on 17.5 JDK versions, from version 5 up to not even released version 22 early access build. Why we do so, we are going to see today. And again, another check. Who knows this tool? You might hate it. It's OK. OK, nice. So sometimes, as we test JaCoCo, we indeed do find bugs in JaCoCo. But I would say quite often we also find bugs in JDK. And we report them back. They get fixed. Some of them not. That's a quite interesting and funny process. Several years ago, there was start of a program, OpenJDK Quality Outreach, where OpenJDK developers contact open source projects and ask them to test early access builds, find bugs, report them back. And we participated we was pioneers of this program. And at that time, we've been actually one of the top contributors of bugs to OpenJDK. And here is a real disclaimer, actually, for today's talk. I'm really sorry. I'm really sorry. There will be a little bit blood out of your favorite Java virtual machine. Sorry for that. There will be naked Java compiler, no ID, nothing, just Java compiler. Strong language. We're going to talk not English, not French, not any other. We're going to talk bytecode. And within, 40 minutes, I'm going to try to do intense violence of your brain. If you're not ready, I think there are other wonderful talks. You can go listen them. If everybody go, I also will listen some other talk. So, are you ready? Yeah, OK. Relax. Take a cup of tea or coffee and enjoy Java. So let's talk about Java. A quick recap. You all probably know that in Java version 8, lambdas appeared. It has been quite a long time ago. So here is a little example with a lambda. We have a method fun, and we declare lambda as a parameter to another method run. Super simple, super easy. Notice that on the line 6, there is a string, hello Copenhagen. Do you know what is going to happen if we compile this? What's going to be inside of your class file? Well, we don't need to guess. We can just compile and decompile and look into the bytecode. This is one of my favorite other tools, which I use not daily, but let's say weekly, JavaP, so-called Java disassembler. We can call it with two arguments, -v verbose and -p, show me privates, protected methods, etc. Basically, as I call it, Java p -v -p, show me everything. So we compiled the class, we decompiled it, and here's what we get. What's there inside? Here is our fun method. Here is its body. But where is a string literal Copenhagen? It was there. It was supposed to be there, but it's not there. Well, there is even more. Where is line number 6? It just disappears. If you know, or if you might know, that all of this is mechanics behind wonderful bytecode instruction invokedynamic. This instruction made it possible to implement lambdas in Java language. And here is a quick recap. Invokedynamic instruction uses a bootstrap method, which uses some other machinery, like in case of lambdas, it uses lambda meta factory to construct an actual call site, which is going to be placed in the place where invokedynamic instruction is used. This call site returns an object that basically holds a real method handle that should be invoked. And, well, it has a reference to a special method generated in your class file. And this method now contains the string that we've been looking for. And it contains a line number 6. This internal implementation details of lambdas, of invokedynamic. This is nice, this is quite performant, but what is going to happen if we're going to try to use invokedynamic for constants? Well, there is an allocation overhead. We should hold in memory a call site. And, well, there is a method invocation overhead. So for constants, it's not that nice to use invokedynamic. And here we go. A new JEP appeared in Java 11, also known as CONDY, dynamic class file constants, that solves these problems. With dynamic class file constants, we get a real constant. It is a less overhead. And we get a more performant execution because it is a constant. Just-in-time compiler doesn't trust final fields. Well, you probably know because of reflection and etc. But it perfectly trusts constant pool entries, and CONDY resolves to the constant pool entry as any constant in your program, like 42 or a string literal. Less overhead. And there is more. To invoke dynamic instructions, they have different linkage stage. When you call one, you need to link this invoke dynamic instruction with some method. When you call another, you need to link this invoke dynamic instruction with another method, or with the same one. But two CONDY instructions, they do share the same linkage stage. Once we obtain it using CONDY, a constant, within the same class file, the same constants are not gonna be any more linkage stage. We already know to what this constant resolves. This is nice. Well, but where this can be used or where it is already used? Let's take a look on another simple example. We have a method. In this method, there is some code written. And let's say we would like to measure code coverage of this method. So let me complexify it a little bit. Let's say that there is some branch, if else, and a simple condition. Let's imagine that we want to record execution of this method and know which parts of it were executed, or in other words, covered by code coverage. What should we do? Turns out it's pretty easy. If we insert in certain positions of those methods so-called props, which record fact of their execution, we can perfectly know which branch was taken. We can say, okay, if prop 0 was executed, then true branch was taken. If prop 1 was executed, then false branch was taken. If both were executed, we know that method has a full coverage, all the branches were covered in it. And all the instructions that led to props were executed as well. So, oops, something went too fast. So, now, what the prop is? Do you have any ideas what we can insert in original class to record its execution? We have some requirements. It should have a minimal runtime overhead. Well, obviously, we don't want to slow down your program that much that testing becomes infeasible. It will be strange. And it should have no side effects on application. So we don't want to turn your multi-threaded application in a single-threaded. That would be awful. We don't want to change values in your code. And it should record the fact of execution. And it should be identifiable. We should be able to say, OK, this point, exactly this point was executed. Do you have any ideas what could be placed there? Well, wake up, people. It's almost noon. Not almost, it's noon. But OK, I hope you will wake up in 10 minutes. Turns out that it's not that hard to satisfy those requirements. There is a very simple basic construction in Java which satisfies all those requirements. Well, almost all, but that's probably a story for another talk. So we can use a Boolean array. And the Boolean array has storage. If you write in this storage true at some index, we simply indicate that probe with this ID was executed. That's it. It's harder to imagine. I spent years trying to find a better construction with a lower overhead. It's harder to imagine anything else. That's simple as it is. But we need to get this array from somewhere. We need to get it in order to record the fact of execution. We need to store it somewhere so that the code coverage tool and Giant can later on use this data and transform it into the wonderful report that you're going to see. So where we can get this one? Well, that's also not hard. We have a Java agent which collects all the information. So this agent can have a method, please give me an array of probes. We're going to call this method saying, OK, we want a record execution of this class. We need that amount of storage, number of probes. And well, here is a special identifier of this class. As you might know, with the same names, there can be multiple classes in the JVM loaded by different class loaders. So we need to identify them somehow. Here is class ID. That's simple like this. And to improve performance, we're going to store this we're going to store this array in a field. And later on in the methods, we're going to actually store it in a local variable. Access to the locals is faster than access to the field. That's it. That's how JaCoCo actually works under the hood. As simple as that. Do you see any problems with this code? For me, it's quite small, but for you, it should be quite observable. I really, really need you to wake up. Do you see any problems with this code? Well, no worries. We also haven't seen problems with this code for many, many years. It worked. So now you should wake up. Now a really hardcore part starts. But I will warm you up a little bit. Let's take a much simple example of the code. Let's say I have some class. Let me call it child. Why not? And in this class, I'm going to have a method which does assertion. Pretty stupid, pretty simple assertion on two constants, 1 and 2, and I'm asking whether they're equal or not. And I'm going to call this method. So are we going to get assertion here or not? No. Why? Who thinks that we are not going to get assertion here? I do think. Who thinks that we are going to get assertion here? I also think. Well, the actual answer, it depends. As you might know, in Java virtual machines, there is a special argument which says enable assertion or disable assertions. We can even enable assertions for particular class or for a package, etc. So if assertions disabled, we are not going to get assertion here. They disabled, they ignored. If assertions enabled, we are obviously going to get assertion here because 1 is not equal to 2. But the answer on the question, well, it depends. Let me complexify example a little bit. I'm going to take one more class. I'm going to call it base. In this base class, there are now going to be a static initializer. And instead of calling original method from my main method, I'm going to call this method from the static initializer of the base class. And now child inherits base. What is going to happen in this case? Are we going to get assertion here or not? It's almost the same example as before. Who thinks that we are not going to get assertion here? You might refer to the previous answer. Yes, if we disable assertions, we shouldn't get assertion here, right? What puzzles you? Well, to answer this question, let's have a look at the Java language specification, our Bible. Java language specification, in this case version 8, paragraph 14.10, says an assertion statement that is executed before its class or interface had completed initialization is always enabled. There is no way to disable this assertion. So the ones who said, yes, we're going to get assertion here, they're right. There is no way to disable this assertion. All others, no problem. Here is a flag for you. This one is always enabled. Why so? Why this happens? To answer this question, we need to have a look at the bytecode again, but I'm going to save a little bit of time, and this is not a bytecode, this is equivalent source code. Basically, compilation of assert statement is equivalent to the compilation of this Java source code. We have some synthetic field added to our class that holds a status, whether assertions disabled or enabled for this class. And we request a runtime. Hey, runtime, could you please tell us, do we have assertions for this class enabled or not? And we store the value that runtime returns to us in this field, and later on, we use this field. This is exactly the same performance optimization that we've been seeing in JaCoCo. It's exactly the same trick. It's too heavy, too expensive to, on every method call, on every assertion invocation, to go to the runtime and ask a status, because there might be synchronization involved, etc. That it's much easier and more performant to ask once and cache the result in a field. But then the problem is the static initializer are going to be executed only when class is fully initialized. And when the class is not fully initialized, static initializer wasn't executed, so field has its default value. In case of booleans, default value is false. So when class is not initialized, condition if not assertions disabled turns true. And it's always enabled. That's why Java language specification says that it's always enabled. This is implementation detail. This is just a quirk of how assertions were implemented in Java compiler. But because of this quirk, they have to put this in Java language specification. If you look at this code, it is exactly the same code that we use in JaCoCo. Look, it's exactly the same. We ask runtime, hey, can you give us array of props? And runtime returns it to us. We store it in the field, and then we use it from the field. It's exactly the same code. So here, when we try to write something while class is not yet initialized, we are going to get null pointer exception, because the default value for objects, for references, for arrays is actually null. That's a problem. What can we do with this? Well, we found a solution quite some time ago, let's say 10, 20 years ago for this. Instead of using a static initializer, we're going to do lazy initialization. We're going to have a method. This method looks if field initialized. If the field is not yet initialized, only then asks the runtime, stores the value in the field, and if field is initialized, well, just return it. Super simple, super easy. This works for this problem of not yet initialized classes. Are we done? Is there some other problems? Any ideas? What is going to happen if you write such a code and try to compile it? Will it work? Exactly. Thank you very much. I haven't seen who said that, but we have a static final field, and we write to it. You can write to static final field only from static initializer. But here we have another method that writes to it. It turns out that while Java compiler doesn't permit you to write a code that writes into static final field from the method, Java virtual machine wasn't doing so for quite a long time, till Java version 9, till OpenJDK version 9. This was not checked on the Java virtual machine level. It was only enforced on the compiler level. And our codes worked for many, many years. We've been writing to a final field from a method. Since OpenJDK 9, this does not work. This throws illegal access error because, well, Java virtual machine specification says you can use a put static instruction only if the field is final, you must use this instruction inside of static initializer, otherwise exception is thrown. That's it. So what can we do? It should be simple. Let's remove final. That's it. JIT anyway doesn't trust final fields. It doesn't optimize them. So what's the problem? Let's just remove final, and it's going to work, right? Do you see problems now? Did we resolve them all? Well, what about interface? You know that quite some time ago, interfaces also got a method, and now they can contain executable code, so we might want to record code coverage in them. And also, you know that in interfaces, every field is implicitly static final. There is no way to choose that it's not going to be final. It's implicitly static final. So it requires a static initialization. Either we need to remove final or we need to remove static initializer. If you don't remove final, we get illegal access error. If you use static initializer, we might go back to the problem of static initialization, right? And we get a null pointer exception. That's a catch-22. What can we do here? Before we do anything with this, let's first figure out whether there is a problem of cyclic initialization and not initialized class, whether there is problem at all to solve or not. So we have interface base, we have interface child extends base, super simple. In the base, we need to trigger initialization. So to trigger initialization, we need to trigger initialization of a child and a base. When class or interface initialized, its superclasses are initialized, as well as all super interfaces that declare any default method. So we need to have a default method in a base. Here we go. Then, in the base, we need to call a method from a child. So we are going to declare a static final field here that creates a child and calls a method on a child, pretty much like with classes. And we are going to declare in the child this method that we are going to be calling. And just to see the trace, why not? Let's throw assertion error exception here without any conditions. We just want to see that this happened or not. And to trace more execution, we are going to add into the child also some field that just prints a child. So if we see here, and the last piece, we need to trigger initialization of all this hierarchy. So let's construct child. Construction of child is going to be triggering initialization of base and so on. And what are the possible outcomes of execution of this program? Well, if we see an exception, assertion error base, it means that base is initialized before child was initialized. That's it. If we see that child is printed on the screen and then we see assertion error, it means that child first initialized and only then base is initialized. So in the first case, we're going to get back to exactly the same problems that we've seen with classes. And in the second case, there is no problem at all to solve, because child, in case of interfaces, is going to be initialized first. Here is again a question to you. What do you think is going to happen? Who thinks that it depends? I do think it depends. You're right. As usual, the answer is, it depends. Imagine our surprise when we've been testing this. We've been in 2 different countries in the world, me and another colleague of JaCoCo. We've been writing exactly same code, independently actually. We've been experimenting with issue reported to us. And we've been using different JDK versions. I don't remember who was using which one. Maybe I was using older one. But basically, on JDK version 8, update 40, prior to this version, you're going to see that assertion error happens and child is not yet initialized. I think it was Mark, another colleague, who've been using more recent version after update 40. Imagine his surprise when he wrote to me, look, I'm getting a JVM crash. He ran exact same code, and what he saw on his screen is first child is initialized, not even exception is thrown, child is initialized, then base is initialized, and then bam, JVM crashes. So here is how we found one more bug in JVM. We reported it back, and it got quite, in a timed manner, fixed. It got fixed quite fast. In 8 update 152, early access build, we tested it. And here is what we get at the end. Before this update where fix happened, we are having the same problem as with classes. Base is initialized first. After update, the actual correct behavior that was supposed to be there always since the beginning, according to the Java virtual machine specification, is actually opposite. It should be child initialized first in case of interfaces, unlike in case of classes. And well, we get some range of virtual machines where such code crashes. Shit happens. So, what can we do in this case? In this case, well, we need to find a solution for our tool. So we cannot remove final, we cannot get rid of static initializer. So we resort to a slower solution. We are going to have a slow pass for all JDK versions. This slow pass will always be calling runtime without caching a field, without storing the value. This has some performance hit, but sooner or later, class will be initialized, so value is going to be cached. This little performance hit is going to be only during the class initialization, which is not that long process, hopefully. And, well, hopefully, JIT optimizes quite a lot. Here is what we get. Oh, sorry. Let's get back to the topic of this talk. Let's get back to the Condy. Condy is such nice addition to the JVM, which allows to get rid of all this magic. We can replace all this dance with static finals and etc. with just one bytecode instruction. We can just load this data from a dynamic constant. And resolution of a dynamic constant is not coupled with static initialization. There is no problem of dependencies, etc. We can use Condy here. It works the same for classes, it works the same for interfaces. There is no more difference of order or any other problem. That's pretty neat, pretty nice. Another side effect, nice side effect, you cannot see dynamic constant as a field in the class. Previously, we've been storing it in a field to get the performance. Now we are getting the same performance just with a Condy. without the trick, and we don't introduce any synthetic field in your class. This is also a nice side effect because users of JaCoCo, of our instrumentation agent, they always surprised that instrumented classes where we record coverage, they do contain some additional member. Reflection, they see this field through the reflection. And it's not nice for serialization frameworks, etc., etc. With a constant dynamic, you don't see it through the reflection. That's nice. There is less overhead, no fields, etc. What was not nice when we implemented this and what we've been, again, testing is it was not entirely tested when it was implemented. Unfortunately, if you've been trying to use dynamic constant on early versions where it appeared, it was leading again to the JVM crash. They tested many cases. They tested dynamic constants of a type object, primitives, etc., but they forgot that there is a Boolean arrays. And this was leading to the crash. Well, we reported that. It got found a little bit later because we've been lagging with testing at that time. But we found it, reported, and it was fixed in OpenJDK 13. Unfortunately, 2 releases after dynamic constants were introduced. But there is a workaround for this, and well, this also was backported to updates of earlier versions, the fix. There is a workaround which we can use for the versions where fix doesn't exist. We just need to use object for the dynamic constant as a type, and instead of storing it directly in the local variable, we need to do a checked cast. A little bit of bytecode overhead, a little bit of runtime overhead, but well, at least we don't get crashes out of this code. Well, then our users discovered another problem. Apparently, JVM can crash when bootstrap method that resolves dynamic constant triggers loading of a class whose static initializer, again, static initialization, remember, it's evil, it's source of many problems, throws exception. We had this pass in our agent because calling an agent might trigger initialization of some class. Some of our classes verifies that configuration is correct. If configuration is not correct, it throws an exception. So we crash JVM. Instead of telling to a user that his configuration is incorrect, he's going to see a crash dump. That's not nice. We need to fix it. Of course, we need to also report it. We found it again a little bit later, already 3 releases past the Condi was introduced, but that's fine. And we have, it was again backported to another updates. This time it was not backported to version 12, because, you know, intermediate versions, they are not LTSs. They stop development on intermediate versions as soon as they switch to the development of a newer version. And, well, we need to find a workaround, well, super simple. Don't throw exceptions, right? No exception, no crash. Well, that's a joke. We still need to show configuration here to the user. So instead of throwing exception, instead of throwing exception in static initializer, we just need to throw exception in not a static initializer. That was as simple as this. Then, again, thanks to our users, not even to us, we don't do extensive testing on all of the JVMs that do exist in the world. We mainly target hotspot JVM. But our users, they do use other JVMs like OpenJ9. And apparently, OpenJ9 got implementation of Condi, but they did a mistake in another place. Not with a Boolean array, they did a mistake with garbage collector. There have been some missing garbage collector barriers, so this was also crashing JVM under some heavy loads. Well, that's got reported. I don't remember when it was fixed, but it was fixed, and the same story, they do backport, so it was backported to the earlier versions. Unfortunately, in this case, we cannot provide any workaround at all, so we left it like this. Let's get back to assertions. You remember this code, which was using assertion, static initialization, field, etc. It's exactly the same code that we use in JaCoCo. If in JaCoCo we could use dynamic constants, then for this code, we also can use a dynamic constant. And we can finally fix this little trick in Java language specification so that we don't need to guess anymore whether this exception is enabled or disabled. We can just replace all of this with a dynamic constant. And there is already bootstrap methods inside of JDK. We don't need to even create such a bootstrap method ourselves. There is plenty of bootstrap method in a package javalang invoke, in a class constant bootstraps. In particular, it's already possible, if you'd like to experiment with dynamic constant, it's already possible to use wonderful bytecode manipulation library ISM and encode dynamic constant in your class file. And here is a code that uses javalang invoke constant bootstraps to ask whether assertions enabled or not for a particular class and store the result of this in a dynamic constant. We can just replace all the assertion machinery with this, and we're gonna get rid of the problem of static initialization. Unfortunately, it's not yet done in OpenJDK. I don't know why. Maybe it was on a plate some time ago. Maybe it was forgotten. Maybe it's not yet done because, well, it's quite a tough process. You need to change Java language specification. Maybe people got used to this problem. And if we flip a coin and change the behavior, we actually surprise them more than they are surprised now. But that's one of the uses for dynamic constants. Oops. Is there any other uses in Java for dynamic constants? Yes, there is. For example, if you have two methods and those two methods use exactly the same method handle as a lambda, for example, they use a predicate string is empty. Current implementation of lambdas is going to use two invoke dynamic instructions for this. They're going to have a different linkage stage. So they both going to require initialization, but they both refer to exactly the same target. If you replace this with a dynamic constant, well, there is less overhead on initialization, and that's it. That's wonderful. Another use for dynamic constants. Let me again try to do a little quiz for you. What do you think? How many constants you can declare in Enum? We can declare 1, 2, 3, 4, but how much more? Till when we can continue? I didn't knew answer on this question actually some time ago, but our users are smart. You are smart. You are our users. They test wonderful examples. They test crazy examples. They came back to us telling how many constants is possible. Based on this, I actually decided to run a little quiz on X, or at the time Twitter. And don't worry if you cannot answer it. Even the smartest persons in the world was not able to answer this question. You might know Heinz. Heinz, who runs Java Specialists newsletter, he gave a wrong answer on this question. He was pretty close, but he was wrong. We don't need to guess. We can just try. We can take this code, compile it, decompile, and see what's inside. Here is a bytecode. It's quite big, but out of this bytecode, the answer to this question comes. So, if you look inside of enums, we would see that every enum constant is going to be declared as a field in this class. And this is part of one of the answers on this question. There is a limit on the number of fields in the class. If you look in the Java language specification, Java virtual machine specification, another Bible, it's going to say that number of fields is limited. If I'm not mistaken, it's usually limited by a magic number 65,536 or 35. And that's a limit how many fields we can have in a class. So no more than that. Then there is another field that holds all the initialized values of enum. It's an array, actually. And as it is array, there is another limit on the arrays. And this was the answer of Heinz. Heinz knew that there is array, so he used this approximation as an answer. Arrays in JVM are also limited, and limited by integer max int, he guessed, but even this is not true. The answer is, again, it depends. In a hotspot JVM, arrays are limited by integer max int -2 or 3. I don't remember. It may even vary from one version to the other. It's, again, internal implementation details. And well, then this code has a method that returns this array of values. You all know this method. If you call enum.values, you're going to get all the values of enumeration. And well, there is a static initializer that is going to do all the initialization of the fields and array. And for you to not scratch your head about this bytecode, I transformed the code into the equivalent Java source code. That's how enums look under the hood. And well, here is a nice thing. We can replace all this initialization with a dynamic constant. We don't need to call a constructor. We can just ask constant bootstraps to call a constructor for us and store this value in the field. We can even replace initialization of array with, again, some condi. So here we are going to have a less instruction in a static initializer. This is, by the way, another factor that influences the answer on the question. Size of a method is limited in JVM. It is limited by, again, 65K instructions. So actual answer on the question is indeed it depends. But on practice with hotspot JVM, you get even less than 65,000 of fields. You get about, I think, not even 32,000. You get much less constants in enum you can declare. But with the condi, you can go bigger. You can shrink the size of a method and get closer to the limit, to the other limits. Where else condi can be used? Let's have a look on the other example. You all know enum switches. They've been introduced when? Okay, who remembers? Everybody uses Java 21. We don't need to remember such little details when which feature was introduced. So enum switch is nice. Actually, it was introduced in Java 14. Oh, sorry. I'm lying to you here. Switch expressions were introduced in release 14, and enum switch has been there since a very long time, since enums were introduced. So switch expressions. If we compile switch expression, if we decompile it, if we look at the bytecode again, here we see Java 14. Here is a switch. This switch is done by something strange. This switch is done by the result of invocation of some method, ordinal, and this switch is done by a value returned from some array that is stored even outside of the class that you had. Why so? If you look at this class that is accessed, where this switch map is stored, it's going to look like this. It's going to have a static initializer. Static initializer initializes switch map. It asks what's the ordinal value of constant true. And in the place of the array of this ordinal value, let's put 1. What's the ordinal value of a constant false? And in the place of array, let's store 2. And then the actual switch looks like this. We look into the switch map, we ask for a current constant, its ordinal value, and then we do switch. This is done like that because you might know that Java has split compilation. We might compile enum constant and the switch separately. We might compile them together, then we might go back and recompile the switch, or we can actually recompile a constant. So at runtime, this code cannot trust the order. It cannot assume that one constant always has a value 1 and another constant has a value 2. It has to assume that we recompile at enum and maybe we flip at the order. But the behavior of this code should not change if we recompile something outside of this code. So Here is another trick in Java compiler that makes the order of this switch stable. We can just ask the runtime of a current value, and compiler provides, using this switch map, a mapping of current runtime value into the value that was there at the compile time. Is there any problems with this code? I'm ready to bet you should now know the answer. Wonderful, that's indeed one of the answers that you should remember. Indeed, I'm glad that you remember it, at least this one. But another one is, well, don't use static initialization. It's a source of all the problems. Okay, not all, some of them. This code uses static initialization. So let me try to explore again the problem with the static initialization. It's much more complex code. In this code, we have enum constant, enum x, and constant a in this enum. We have constructor for this constant. In this constructor, we have a switch by another enum. In the other enum, we also have a constant. And just in case, why not, we will need this method ever. We have a method, never call, which we actually never call. But this never call method also has a switch. So the first switch is by another enum, the never call method, the second switch is by a first enum. And we never call this method. What will happen? Yeah, you can answer, it depends. But no, what is gonna happen is actually null pointer exception. And wrapped into exception initializer in error. There is not cyclic initialization involved in this case, in this example. What happens in this case is a little bit more complicated. If we map the exception stack trace to the source code, it's gonna look like this. The part of this stack trace actually points us on a method that is never called. There is no single call of never call method in this program, but the stack trace is gonna point on it. Let's have a look at the bytecode. And well, by the way, if you use Kotlin, here is a similar example with Kotlin, with enums, switches in the Kotlin. And there is no single nullable type in this program. There is no single null value in this program. And somebody some time ago told me that there is no null pointer exception in Kotlin. Well, there is. The problem comes again from internal details of implementation of this compiler trick that generates a switch map. So there is a static initializer in our enum. This static initializer calls constructor. In this constructor, we have a switch. This switch is by switch map that compiler generates for switches to map enum constants. So we need to trigger initialization of this switch map class. Here it is. And this switch map class actually holds switch map not just for one switch, it holds for them all. Even for the ones which are not executed, even for the ones that are never executed. And that's exactly what is happening. Initialization of this unused switch map out of one is unused out of two wants to get how many values in the other enum constant. But the other enum constant is not yet initialized. And we get a null pointer exception. Why we're talking about this and Condi? Well, because exactly the same switch by enum, all this machinery, all these tricks, all these calcs in Java compiler can be replaced by a single constant dynamic instruction. We will need to introduce a new bootstrap method. Unfortunately, in this case, no existing ones work for us, but well, it's possible. I don't know yet, I don't know why this hasn't been done yet in OpenJDK. Maybe again priorities, maybe people again learn it to live with this trick. Is there any other examples of Condi? Yes, there is other. For example, can you tell me what is a good singleton factory? It should be much simpler questions than all the previous ones. This doesn't touch bytecode at all. It depends. Yes, yes, you're right. So let's say we can use static final, right? It's possible in some cases, it's valid answer. If you don't need lazy initialization, we can have static final. We can use synchronized accessor, right? That's probably not what we like to write, but well, maybe in some scenarios, why not? The better probably will be double-checked locking, right? But this one is harder to remember, harder to write, harder to not make a mistake. You need a volatile, you need quite some synchronization, quite some ifs. It's easy to do a mistake in this one, right? No, that's also a valid answer. Another one which I like, which has its own pros and cons, which is easier to remember than double-checked locking, is initialization on demand holder. Well, also a possible answer. Might suit your needs, maybe not. Well, if you use Kotlin, there is even nice thing. We can say all the properties that we want. We want laziness, we want singleton, etc. And we want safety, thread safety, so we can tell it. And well, here we go. There is a JEP draft for lazy static final fields. This feature could use Condy to bring lazy initialization of static final fields into the Java. You can use Condy. You can get all the benefits out of it. So maybe one day we will get answer on this question like this. Maybe we will be able to use a new keyword lazy or const or something like this. Let's hope. And there is even more. Java 11 gave us dynamic class file constant. Java 12 gave us JVM constants API. There is not yet implemented JEPs like JEP 333 intrinsics for LDC and invoke dynamic instructions, so that you would be able easily manipulate with this from the Java code without the need to use bytecode manipulation. And here we come to the takeaways of this talk. One, I already know you remember it, and this is wonderful. Quite often, answer on many questions is, let's all together. It depends. Another takeaway that I'd like you to take home, just one more, if you can. Today, new powerful Java and JVM features arrive with incredible pace, with incredible speed. Every day something happens very quickly. They unlock new possibilities. They unlock some other new features that you can use. Not only for Java, not only for JVM, also for other languages such as Kotlin, Scala, Groovy, etc. But you know, people who write this code, they're people. They do mistake. So let's help them. Don't wait, please don't wait. Don't be afraid to try out new features. And when you try out, don't be afraid to report any feedback that you get. Crashes, bugs, whatever. Before the next LTS. It would be wonderful if all we together could deliver a better LTS. If you don't report bugs, the next LTS might be not that great as it would be if we would report bugs. It's actually easy. You found something strange, you found something that doesn't behave as per specification, as per Bible. You can just go to mailing list and write this. Or you can go to bugsjava.com and report the bug. If you get a JVM crash, just attach this JVM crash to this bug and with a little reproducer. And the people on other end will take it, will investigate, and will provide a solution for the good of all of us. And don't be afraid. Don't hesitate to provide not only bugs and crashes. Don't be afraid to say thank you to the other developers, to the developers in particular of open source projects, to the developers who are not paid to do their job at night, to deliver you some open source tools that you use, or, well, if you hate them, yes, don't say thanks to them, but they sleep less than others to find some strange bugs and to give you these open source tools. So don't be afraid if you like their tools, their work, to say thank you. Because those guys, they do deal with only negative feedback, something doesn't work, something crashes, etc. But sometimes they would like to hear a little thank you. So that's it. Thank you very much for listening.